Welcome to a lesson on the law of sines. In this lesson, we'll be looking at how we can first find the area of a triangle if we're given two of the sides of the triangle and then the angle in between them. And then we'll actually get into the law of sines. We'll define what the law is. We'll look at some cases when we can use it to solve a triangle. And remember, solving a triangle means that we're trying to find any missing angles and lengths of the sides. And then in particular, there's one specific case we need to look at, which we refer to as the ambiguous case. So we'll just kind of explore some of the different scenarios that might result in. So first, let's look at the area of a triangle. We know just kind of from basic geometry that the area of a triangle can be computed using the formula 1/2 the base times the height. If you remember, the base and the height have to be perpendicular to each other. So in the two illustrations that I have here, we have an acute triangle and then an obtuse triangle. And in both triangles, we have a base measure, which we can call B. And then we have to also have the perpendicular height of the triangle perpendicular to that base. So using just some right triangle trig, we're able to convert that formula 1/2 base times height to the formula area equals 1/2 a times b times sine of theta. So the a and the b are the two sides, and theta is the angle that's in between the two sides. So let's look at an example. Let's find the area of an equilateral triangle if we know that the sides have length 12 inches. So an equilateral triangle, again, means that all of the sides have the same length, and it also means that all of the angles have the same measure. So we know each of the sides is length 12 inches, and then we know all the angles are the same. So if there's 3 angles, and we know it has to be 180 degrees, 180 divided by 3 is 60 degrees. So the measure of each angle has to be 60 degrees. So to find the area of this triangle, again, in sort of the old-fashioned way, we'd have to figure out what's the height of the triangle. But now we can just think in terms of two sides and the angle in between them. So area is 1/2 the a and the b, which the letters a and b don't matter, but it's just the two sides that we're given. So in this case, since it's equilateral, they're both 12, times the sine of the angle in between, and since all the angles are the same, it'll be the sine of 60 degrees. And so we have a half. 12 times 12 is 144, and then the sine of 60 degrees would be √3/2. And if we multiply that a little further, half of 144 would be 72, and then half of that would be 36. So we'd get 36√3, and that would be in square inches. All right, so now that we've finished that, let's go ahead and look at what the law of sines are. So we define law of sines sort of with ratios or proportions, where we are relating the measure of each angle with its opposite side. So if we look at the sine of angle A and the sine of, versus its side A, so again, angle A, again, we could draw any triangle we want. We don't even have to use the letters A, B, and C, but just for this example I will. But angle A is here in the bottom left corner. Side A is all the way across the triangle. So we're always going to talk about an angle and then the side that's always opposite the triangle from that angle. And so in similar fashion, we can have a sine of angle B and a side B, and then we can have sine of angle C and side C. So what the law of sines tells us is that the ratio between the angles and the sides has to be the same for all 3 pairs. So kind of a sort of intuitive way you could think about this is whichever angle is the smallest, it's going to have the shortest corresponding side. So if in this illustration I have angle A is the shortest, the narrowest angle, the least rotation, and that corresponds opposite side with side A, which if you compare all three sides, side A is the shortest side. And in similar fashion, kind of in the reverse, angle C is the largest angle in this triangle, and side C is the longest side. So the law of sines is just giving us a nice relationship that we can use, relating the angles and their opposite sides, right? The smallest angle goes with the smallest side, the largest angle goes with the largest side. So it's just giving us sort of a proportionality in the dimensions of our triangle. And so again, the law of sine equations that we're looking at, it's three ratios and they're proportional to one another. So the sine of A over A has to equal the sine of B over B, and that's all equal still to the sine of C over C. Now when we talk about the law of sines, there's again kind of three types of scenarios that we might face. And again, when we're talking law of sines, we're trying to solve a triangle, so we're going to be given parts of the measures of the triangle, like maybe an angle or a couple angles on the length of a side, or maybe all three angles or all three sides. So we're going to given parts of the measure of the triangle, and we need to find some or all of the rest of the triangle. And so how we use the law depends on what part of the triangle, what parts of the triangle we're given. And depending on, it could even tell us that we have to use a different law instead of just the law of sines. So there's three particular laws that we're looking at. The first one we'll just refer to as angle, side angle, which you may see abbreviated as ASA. And so in this situation, we are given the measure of two angles and the side that's in between them. So looking at the illustration I have, we know we have a length of a length of 15. And then we're told the angles on either end of that edge of that side of the triangle are 30 degrees and 40 degrees. So I don't know the third angle, and I don't know the length of the other two sides. But because I know the length of 15, and then I know the two given angles, we can actually figure out, we actually have a triangle, and we can figure out what its missing parts are, what the other missing angle and the lengths of the sides would be. Another situation which is very similar, but we sometimes might refer to this as side angle angle, so SAA, or you may see it reversed and say angle angle side. So the difference here is we're still given two angles and a side, but the difference is that the side is not connecting, it's not in between the two angles. It's one of it's one of the other two sides of the triangle. So again, in the illustration I included, we know we're again given two angles, 30 and 40 degrees, but we're not given the side of the triangle that connects those two angles. We're given one of the other two, so in this case a length of 8. But again, given those three pieces of information, that's enough for us to, if we could get a ruler out and draw, and get a compass and protractor, we could sit down and we could draw, we could figure out how far apart the 40-degree angle would be from the 30-degree and the side of length 8. So we could figure out what the triangle would look like, and we could figure out the missing values. All right, in the third case, we refer to this as side-side angle. Students like to use that in reverse, but we'll keep it as side-side angle. And put a little asterisk here, we often will refer to this as the ambiguous case. Ambiguous means that there's no, it's not always clear what our solution is going to look like. And so we're going to have to explore this particular case a little bit more. But the idea is we're given two sides. So say we have two sides of a triangle, one is length 8 and the other is 15. And then we're given the measure of one of the angles, but it's not the angle in between the two sides. Okay, it's one of the other two angles. And so, and we'll explore this more, but because of the type of information we're given about the triangle, it may not be possible to actually draw out a triangle that fits the given numbers. So we may not be able to draw a triangle that has two sides of length 8 and 15 with an angle of 40 degrees. We might be able to, we might not. We might be able to draw one triangle, we might be able to draw two triangles. Okay, and so those are kind of our options. There could be no triangle, one triangle, or there could be two triangles that we could have to figure out. And so it's, again, it's not clear just from the numbers what our triangle is going to look like. And so we'll explore this more as we go forward. For now, though, let's just look at a couple examples using angle, side, angle, and angle, angle, side. Through most of these examples here, I've used kind of the same triangle setup, just this triangle ABC. But all of the stuff that we're going to do, the letters, you don't have to use A, B's, and C's. You can use whatever letters you want. The triangle doesn't have to be drawn in the same position and shape that mine's drawn in. It can be whichever format you want. I'm just using the same image here. So in this example, we have, again, triangle ABC, and we know angle A is 40 degrees, and we know angle C is 65 degrees, and then we know side B has a length of 20. Now, just before we go further, before we actually do anything, I just want us to look at the information we're given and realize that it is an angle, side, angle. We are given an angle and a side and an angle, and the side is the side that's in between those two angles. So from that information, we do know that it is angle, side, angle. And again, this is important. This should always be your first step when you're working with these triangles, because you need to know what kind of triangle, what kind of information you're given. Because right now we're only doing law of sines, but in our next lesson we'll look at law of cosines, and we're going to have a similar setup, but the categories are different. So we need to be able to distinguish, are you going to do law of sines or are you going to do law of cosines? And if it is law of sines, is it the ambiguous case, or are you going to have a nicer problem to work with? So again, in this example, we're given the information that would give us angle, side, angle. So again, for this problem, we just want to solve the triangle, which means to solve triangles, we're looking for the remaining parts. And so in this example, we need to figure out what is angle B. So we need to find angle B, and then we need to find sides A and C. So those are the pieces that we need to find. Angle, side, angle is really easy because we have two of the angles, and so it's really easy to find the third angle. So again, to find B, we know that the sum of our three angles must equal 180 degrees. And we know, so A plus B has to equal, A plus B plus C has to equal 180 degrees. And we already know A is 40 degrees. B we don't know yet, so what we're trying to find, but we know C is 65 degrees. And so we can just do a little bit of algebra here. So we get B plus 105 is equal to 180. And if we subtract that, we're going to get B is 75. So we know B, we've already found the third angle, it's 75 degrees. Okay, so all that's left is to find our two sides. And this is where the law of sines is going to come into play. So in order to use law of sines, you have to have at least one pair of angle and side. So in this example, we now have angle B and side B, so we can start using that. So let's just sort of go alphabetical. So we know the sine of angle A over the length of A must equal, and we're going to use our pair here, we're going to use the sine of angle B over side B. Okay, and we're trying to solve for side A. So we're going to have the sine of angle A, which is 40 degrees, divided by A will equal the sine of 75 degrees over 20. So these are really easy to solve. They're just proportions, so we're just going to cross multiply and divide. So we're going to multiply diagonally. So you're going to have 20 times the sine of 40 degrees will equal A times the sine of 75. And then we're going to divide the sine of 75 over. So we have 20 times the sine of 40 degrees divided by the sine of 75 degrees, and that has to equal A. Now, if the 40 and 75 degrees, if those were nice unit circle angles, then we could easily go ahead and compute their sine values just using the unit circle. But in this case, they're not, so we'll need to use our calculator, which if we do that, we get that A is going to be 13.31. And that's rounded to 2 decimals. So we now know side A as well. It is 13.31. So all that's left is to figure out C. To do C, it's going to be the same setup. You still want to use the same pair, so the B values. You don't want to use the A values because we just rounded side A. So we want to use the B values because those are exact. So we're going to have the sine of angle C over side C, which has to equal the sine of angle B over side B. So we have the sine of 65 degrees over C, and that'll equal the sine of 75 degrees over 20. We cross multiply, so we're going to have 20 times the sine of 65 degrees, and that's equal to C times the sine of 75, which means C has to equal 20 times the sine of 65 degrees divided by 75 degrees. And again, we'll want to compute that using our calculator. And notice that this computation is very similar to the one we just did. The only thing that's different is instead of sine of 40 degrees, it's now the sine of 65 degrees. Everything else has changed. And so in this case, we get 18.77. So we've completed our triangle. We were given angles A and C and side B, and we have now found sides A and C, which again C is 18.77, and then we found angle B. So we have solved the triangle, and this was an angle side angle triangle. All right, let's try another one. So again, same setup, triangle ABC. Again, we can use whatever letters we want, but let's say this time angle A is 20 degrees, angle B is 75 degrees, and side A is 15. Okay, so again, the first step is to identify what kind of triangle we have. So we are given an angle and another angle and a side. So just like in the previous example, we had 2 angles and a side, but this one's different. We don't have the side that's in between the 2 angles. If we were given side C is between angles A and B. That would give us angle side angle. So in this case, it's a little different. We're actually already given the pair for the A's. So we know angle A and side A. So to some extent, we could go ahead and find side B right now. But let's go ahead and find our angle. So the process for this is going to follow almost exactly the same. So we need to, let's go ahead and find angle C. And again, we do that using the sum of our 3 angles, which has to be 180 degrees. We know A is 20 degrees, B is 75 degrees. So that would be 95 degrees plus C has to be 180, which means C is going to equal 85 degrees. Okay, so we already know angle C. So all that's left is figuring out side B and side C. So let's go ahead and I like to go alphabetical if I can, but you don't have to. So let's do side B. So we're going to try and do the sine of angle B divided by the side B. it has to equal, and again, the pair that I'm currently given is the a's. So we're going to have to do the sine over side a. And so that's going to be the over b, which is equal to the sine of 20 degrees, which is equal to the sine of 20 degrees over 15. We cross multiply, and that gives us 15 sine of 75 degrees is equal to b times the sine of 20 degrees. And then we're going to divide, so b is going to be 15 times the sine of 75 degrees divided by the sine of 20 degrees. And that turns out to be 42.36. All right, so we know side B is 42.36. So we just have to do side C. So again, we know our pairs. We're going to do A and C. So sine of C over C has to equal the sine of A over A. And you can write these fractions in whichever order you want. It doesn't matter. But that's going to be the sine of 85 degrees over C. And that has to equal the sine of 20 degrees over 15. Cross multiplying gives us 15 times the sine of 85 degrees, which is equal to C times the sine of 20 degrees. So C is going to be 15 times the sine of 85 degrees over the sine of 20 degrees. And again, this is pretty much the same computation we saw in the last example, but because we're using angle C, we're going to have 85 degrees instead of the 75 degrees that we had with B. And so our result that we get here is 43.69. Okay, so I kind of mentioned this when we were talking about what the law of sines represented, and I skipped over it in the last example. But now that we've finished the triangle, let's just kind of look back at how the angles and the sides compare to one another. The smallest angle that we're given is angle A. It's 20 degrees, and it's significantly smaller than the other two. It's almost 3 times, 4 times smaller than the other two angles because we have 20 degrees, 75, and 85. So it's about almost a quarter of the size of the other two angles. So it's 20 degrees. So angle A is the smallest angle. So which side should be the smallest? Well, if A is the smallest angle, side A should be the smallest side. So look at the comparison in the sides. We have side A was 15, and then sides B and C were both 40. And so again, side A is significantly smaller. It's almost a third of the size of the other two sides. Okay, so again, we're kind of seeing that that proportionality in our angles and sides. And we could do the same thing. Side C, or sorry, angle C. Angle C is 85 degrees, and it is the largest angle. And side C, which is 43.69, is the largest side. We could go back and look at the last example. We knew that, again, angle A was the smallest at 40 degrees, and side A was the smallest at 13.31. Angle B was the largest side, it was 75 degrees, and side B was the largest side at 20. So again, that proportionality that we see plays out after we get through all of our work here. All right, let's try one more here. So we were given, this time, same setup, triangle ABC. We want to solve it, and we are told that angle A is 40 degrees. We are given side B is 15 and side A is 6. So again, we want to sit down and make sure we recognize what kind of triangle this is. We are given an angle, and 2 sides. So this one's a little different. In the past, we were given 2 angles. So this time, we're only given 1 angle, and we're given 2 sides. And so you need to ask, where is the angle? Is the angle in between the 2 sides, or is it not? So in order to be between side B and side A, you'd have to be angle C. So angle C would be in between the 2 sides. Side A is not. So this is then a side angle triangle, which again we refer to this as the ambiguous case. We don't have to, but if you hear that phrase, ambiguous case, you need to know this is what we're talking about. So let's go ahead and see if we can solve the triangle like we've been doing. So let's look at the pairs that we have right now. I know I already have the A's, so I know I could do the sine of A over side A. And then I already have the length of B, so let's try and find, let's do our B ratio. So sine of B over B. Now let's plug in the values we have and see what happens when we compute this. So we're going to have the sine of 40 degrees over 6, and that has to equal the sine of B all over 15. Just pause here for a moment. Just like we've done in the past 2 examples, we're trying to find an angle first. But this one's a little different. In the previous 2 examples, we could just find the angle by adding up the 2 sides and adding up the 2 angles we were given and subtracting it from 180. We can't do that this time because we're only given one of the angles. So we're going to have to pair it up with a side. The other thing that you should notice even at this point is we are trying to find B, angle B. And B is inside the sine. So how do we get rid of a sine? We're going to have to do an inverse sine. Okay, so just keep that in mind as we're going through what we're going to end up seeing as we go through this. So to get B by itself, we first need to multiply the 15 over it. So we're going to have 15 times the sine of 40 degrees over 6. And that's equal to the sine of B. And so again, if we kind of like taking square roots of both sides, we're going to take the inverse sine of both sides. So B will equal the inverse sine of the other side of the equation, the 15 sine of 40 degrees over 6. And let's go ahead and compute what that fraction is. So we're going to have to compute the inverse sine of what? Well, if you take 15 times the sine of 40 degrees divided by 6, you end up getting 1.60697. We'll go a few extra decimals here. Okay, and so we need to compute that. What that is, so what's the inverse sine of that? So what is the inverse sine of that 1.60697? Well, depending on what kind of calculator you're using, it might spit out like some sort of domain error or maybe a non-real result, something like that, or no solution, or it just may say error. But the key here is that there's no answer. Okay, and if you remember back to when we talked about our inverse trig functions, when we talked about inverse sine, what was the domain? What did the inside need to be between? And so we knew that if you had, if you're just looking at the inverse sine of x, we had a domain that ranged from a negative pi over 2 to a positive pi over 2. Okay, which pi over 2 is a decimal, would be about 1.57. Okay, so our domain has to be from negative 1.57 roughly to a positive 1.57. Anything outside of that range of values won't work. And so if you look at what we're trying to compute here in this example, we're trying to do 1.6, which is outside of this 1.57 domain. and it won't work. Okay, so why doesn't it work? What does that mean? Well, in short, what it means is there is no triangle with the given measurements. Okay, so there's no way that we can draw a triangle where one angle is 40 degrees, the side next to it's 15, and the side opposite it is 6. There's no way we can do that. Okay. If this was in the real world, then you would have to go back and remeasure your angle and your sides. Okay. Maybe a mistake was made or something like that. But just from the pure math side of things, um, there's no solution to this. Okay. So let's look at why there's no solution. Here's a GeoGebra illustration, which you can Google these and find these online. Um, but so in the example we're looking at, we are told angle A is 40 degrees. We are told side B, which is one of the sides of angle A, it is 15. And then we're told the opposite side is length 6. Okay. What we are not told is what is the measure of the angle at the top. So what's angle C? We don't know what angle B is, which would be over here on the right, and we don't know the length of the bottom side. We don't know the length of C. So all we know is angle A, side B, and side A. So what that means is that side A doesn't have to point to the right. It could be maybe pointing over here and making angle C a really small acute angle. Okay, so it can rotate back and forth. I don't know where it's at because I don't know what the size of its angle is, and I don't know where it's supposed to connect to the bottom side. Okay, so we're kind of in this unsure phase right now. But with this particular example, even more importantly, A is only 6 units long. What's not happening? In order for me to have a triangle, this has to reach down and touch the bottom side, and it's not. It's too short. Okay, in order for it to connect, it would have to be about 9.6. So if I could draw it straight down, we could actually, so if side A, if I changed the problem and I made the length of side A to be 9.6, it would actually create a right triangle. Okay, and so we could actually then get a solution, but it would just, we could use our right angle trig type stuff to solve it. Okay, so if the opposite side, so here's one thing to remember, and we'll kind of summarize all this a bit. If the opposite side is too short, and what I mean by that is if it is shorter than the height of the triangle, then it will not connect. You will not get a triangle. Okay, so we have to have it long enough. If it's too short, we don't get anything. So again, if we made it exactly 9.6, now when we try to connect, it is just barely long enough. We might actually have to round up and go to 9.7 or 9.6 and a half, something like that. But we could find the exact length, with some approximation to figure out what right triangle we would have. Okay, so next question is, what happens if the opposite side is long enough, but not too long? So let's say I changed the problem, and I said, side A, sorry, angle A was 40 degrees, side B was 15, and side A was 11. Okay, so notice now it's too long. It has to reach down and touch the bottom side. And right now it's sticking through the bottom side. So that means I need to move the angle of my line, and I could move it to the left or to the right. Either direction would work. So if I moved it to the right, okay, what do we get? Oh, we just got a triangle. Okay, so we do have a triangle if I move that to the right side. Again, we can go through and compute what all these values are, but we can find angle B, we can find angle C, and we can find side C. So we could actually solve this triangle. Okay, but we could just as easily go to the left and make a triangle here. Okay, and this is a completely different triangle. I mean, it's completely different, except for the angle A, side B, and side A. Okay, this is an obtuse triangle. The angle B is 118.7 degrees. This over here, if we go back to the right, this is an acute triangle. There's no obtuse angles, right? And so again, we can have different options about which triangle it is, okay? And then one other option that we need to worry about, what happens if the opposite side was a bit longer? Okay, so let's go up to, yeah, we can't change that. Yeah, what happens if we make it 15? So notice now it's equal to the length of the adjacent side. So I could go ahead and stretch it out here and create my triangle. In fact, it turns out to be it's going to be an isosceles triangle because both A and B are 40 degrees. But what happens if I try to rotate this to the left? I don't have a triangle. I just have two lines sticking out and then one line sticking along the bottom. Okay, so it doesn't create a triangle. And what if the adjacent side was shorter? Right? So say it was 14 instead of 15. So I could stretch it out to the right and get a triangle again. But if I tried to go to the left, it's never going to hit that line again. So because the line's not extending out here to the left, it's going off to the right. So again, if the opposite side, so if side A is longer than side B, we only get the one solution where the triangle goes to the right. Okay, and so those are kind of the situations, and there's a few other things we'll look at. If angle A was obtuse, for example, what are the implications that has? So let's go ahead and go through the different options and summarize what we're looking at. Okay, so let's start with an acute angle. So say angle A is acute, and if the following is true, so if side A is less than H, if that's true, so if we have an acute angle and the side opposite our angle, so again, don't get so attached to the letters. I'm using angle A and side H and B and C and stuff like that, but think more in just in general sense. So, but again, using our example, if I have an acute angle A and if opposite side A is shorter than the height, there's no solution. Okay, so in a more general sense, if the side opposite your angle is too short, if it's shorter than the height, there's no triangle because it's not long enough to reach down and touch the bottom side. All right, the next example is, again, you have an acute angle A, but what happens if the opposite side is equal to the height? Well, now we have one triangle. In fact, it's a right triangle, so you can just use your right triangle trig to solve it. The next one is the worst case. So what happens if the length of the opposite side is longer than the height, but shorter than the adjacent side? This is the one where we're going to get two triangles. Okay. Now just to pause here and look at what these two triangles are. So you have one big triangle, right? So from angle A it goes up side B and then it goes down to the right along the black line here. And then you have the bottom. So that's one, is the whole big triangle. The other option is the smaller triangle, which is on the left half of the graph. So it is inside and you have this obtuse angle at the bottom. So this is the second triangle that we deal with. Okay. Now in the picture there's actually several other triangles, but the third one is important because we could swing side A either to the right or to the left. The triangle that is formed inside those two side A's, again, whether it's the big triangle or the small triangle, the triangle here inside those two sides is actually an isosceles triangle. So that means because they both have side A on the left and the right sides. So if we could figure out this bottom angle here, it has to be equal to the bottom angle on the left, and that bottom angle is supplementary to the obtuse angle that's inside. Okay, so that's going to be kind of how we get to it, and we'll walk through that example. But remember, we have these two triangles with this third sort of isosceles thing that lets us connect the two together. All right, so let's get a little easier here. Again, if we're still talking about an acute triangle, and we know that the opposite side is longer than the adjacent side, then again we only have, and it actually could be equal to it. Well, sorry, if it's longer than the adjacent side, we only have one solution because you can't swing it back to the left. All right, and we looked at that kind of illustration. If A and B are equal to each other, there's no triangle. Okay, we didn't talk about this in the illustration, but what happens if A is obtuse? Well, if if the opposite side is shorter, so if side A is less than or even equal to side B, there's no triangle. Okay, it's not long enough to connect down to the bottom edge of the triangle. So again, that's sort of a nice from an algebra standpoint. There's not a lot you have to do. Just say there's no solution. But if this was a real world scenario, that means you're going to have to go back out and measure all your triangles and stuff. And so the only other situation we have to worry about if angle A is obtuse is what happens if A is greater than B. So what happens if the opposite side is longer than the adjacent side, and in that case we have just one triangle to worry about. So again, the options are, it could be there's no solution, there's no triangle that fits our measurements. There could be one triangle that fits our measurements, either because it's actually a right angle, or maybe it's an obtuse triangle now. So there's several options that we have for getting one triangle. Or it could be that there's two triangles. Okay, if there's two triangles, we need to solve both of them. So it takes a lot of work to get both of them. All right, so let's go ahead and look at a couple triangles where we actually do have a solution. So in this example, again, it's the same triangle setup, triangle ABC. And in this example, we're going to start with angle B. And we're given angle B is 120 degrees. I know side B has a length of 22. And I know side C is 14. Okay, so just like we've been doing so far, let's first analyze the triangle, look at what we're given. So I'm given one angle and two sides, and the angle I'm given is not in between those two sides. If it was in between the two sides, it'd have to be angle A. So okay, so right off the bat, I know that this is a side-side angle triangle. Okay, so we're going to have to work with it that way. So let's go ahead and get as much of this done as we can. I guess we could even figure out, does this have a solution at all? Okay, so first let's look at our angle. This is an obtuse angle. Okay, so we know B is obtuse. Okay, how many options did we have if it was obtuse? There's only two options. There either is a triangle or there's no triangle. We don't have to worry about the two triangles. So the question is that we have to ask, is the opposite side, how does it compare with the adjacent side? Okay, so in this case, the 120 degrees, the opposite side is side B, that's 22. So we have a length of 22. The adjacent side would be the 14. So how does that compare? Well, obviously 22 is bigger than 14. So what did we say if the opposite side was greater than the adjacent side? That told us that there had to be one solution. Okay, had those numbers been flipped around, there would be no solution. Okay, and again, notice that I'm not using A in this case. I didn't talk about angle A. I haven't really referenced, when I talk about opposite and adjacent, I'm not even referencing letters. It's just opposite and adjacent, right? So what we talked about in that previous summary works for any triangle, not just A, B, and C. Okay. All right, so we know we have one solution, so let's go ahead and solve for it. So what pair do we have? Right now we have angle B and side B. So there's my pair, and we're also given side C. So we're going to have to start and find angle C first. So we know the sine of angle C over side C must equal the sine of angle B over side B. So we know sine of C over 14 must equal the sine of 120 degrees over 22. Okay. We're going to multiply the 14 over. So we have the sine of C would be 14 times the sine of 120 degrees all over 22. And then we have to take the inverse sine of that. So we're going to have C is equal to the inverse sine of 14 times the sine of 120 degrees all over 22. And again, we're going to have to just go to our calculator for that. And that's going to give us 33.44 degrees. Okay, so we now have angle C. It's 33.44 degrees. Now that's rounded, so normally I wouldn't use that, but we're going to have to get the other information that we have. So we first find one of the angles. This angle we can now use to find the third angle. So again, we know A plus B plus C has to equal 180 degrees. We don't know angle A, but we do know B is 120 and C is 33.44 degrees. So if we combine those, we'll have A plus 153.44 has to equal 180 degrees, which means A is going to be 26.56 degrees. Okay, so we now have all three angles. So we have angle A, we were given angle B, and we already solved for angle C. We already have sides B and C, so all that's left is to find angle A, and again, or side A, and we're going to have to use angle A to do that. So we have the sine of angle A over side A is equal to the sine of angle B over B. So we have the sine of 26.56 degrees over A. That will equal the sine of 120 degrees over 22. Cross multiply and divide. I'm just going to jump through that here real quick. So to find A, we're going to have to compute 22 times the sine of 26.56 degrees divided by the sine of 120 degrees. And that turns out to be 11.36. Okay, so we've figured out all the missing parts of the triangle. Just kind of as we did in the previous examples, let's just check to make sure that our proportions line up. Angle B obviously is the largest angle, it's 120 degrees. Is 22 the longest side? 22 versus 11 or 14. Yes, 22 is the longest side. Okay, it's almost double the other two, either of the other two. So it's the longest side, goes with the longest angle. Which angle is the smallest? Well, again, it's not B. Angle A is 26 degrees, angle C is 33, so angle A is the smallest angle. So that means side A better be the smallest side, which 11.36 is smaller than 22 and 14. So, this is not a guarantee that I've done the problem right, but it is hopefully a conclusion that I have not done it wrong. Okay, so our proportions do match up. All right, so that was an example of an obtuse triangle. So with side-side angles, we've seen one example where the triangle didn't work out because the opposite side was too short. And then we just did one where it was an obtuse angle. And so we had one solution. Okay, so let's try one more example. And again, I'm just going to give you a heads up. This one's going to take a lot of work because it's going to have two solutions. But let's go through the whole process. Again, we have triangle ABC. We are given angle A is 50 degrees. We are told side A is 68 and side B is 75. Okay, so first things to check, two sides and the angle that's not between them. So this is definitely side-side angle. It's an acute angle, so it's not obtuse. So with acute angles, we have four options that we have to look at, or basically four options. The first is we want to see what is the length of the height, or what is the height of the triangle. And the height, when we talk, there's different ways you can measure the height. You can measure height out of all three angles. We want to measure the height out of the angle in between the two sides that we're given. So again, angle C is the angle that's between my two sides. So I want to measure the height coming out of that angle to the opposite side. I don't care what the height is out of A or what the height is out of B. Okay. So if you notice, when we draw this perpendicular height, it creates a right triangle on the right side and on the left side. And since we're given the angle A on the left side, we'll use that side. So just to quickly compute that, we know, let's do it up here. We know that the sine of angle A is 50 degrees. So sine of 50 degrees has to equal the opposite over the hypotenuse. Okay, so H must equal 75 times the sine of 50 degrees. And if we compute that, you can just, again, use your calculator. So we have 75 times the sine of 50 degrees. That turns out to be 57.45. Okay, so let's just compare it. The height is 57.45. The opposite side is longer than that, at 68, but it is shorter than the adjacent side. Okay, so we're in a situation where we have the height is shorter than the opposite side, and the opposite side is also shorter than the adjacent side. And whether good or bad, that means that we're going to have two solutions, and we need to find both of them. So what I mean by two solutions is we have two triangles that we're going to have to work with. Okay, that means in one example we're going to have the original triangle I drew. So angle or side A goes to the right. Oops. It also means we're going to have another triangle where side A goes to the left. Okay, so we're going to have the big triangle, the whole thing, and then we're going to have this kind of sliver over here on the left. And we have to figure out both of those. Again, I mentioned this earlier, but the relationship between the big triangle and the little sliver is this isosceles triangle kind of off on the right middle section here. So again, angle A, or side A is on the left and the right side of this isosceles triangle, which means this angle here, angle B, has to be equal to this. Okay, so what I'm going to do is I'm going to change this a little bit. I'm going to call this B1 for the first triangle, and then over here, so if this is also B1 here, it's a supplementary angle, which is on the other side. We're going to call this B2. Okay, and B1 plus B2 has to be 180 degrees. Okay, and that's a key we're going to use here in a bit. B1 plus B2 must equal 180 degrees. Okay, and we'll look at that to get the other triangle. So for now, let's go ahead and use our first triangle, and hopefully I can squeeze all of this in here. So we know we are given the pair of A's, so angle A and side A. So we have sine of angle A, which is 50 degrees over 68, must equal the sine of B, and again, we're going to talk about this as B1 over 75. So if we do a little bit of math here to find angle B1, we're going to have to multiply the 75 over. So we have 75 times the sine of 50 degrees over 68. And since we're trying to, that's still the sine of B1, we're going to have to compute the inverse sine. So we're going to have to do the inverse sine of 75 times the sine of 50 degrees all over 68. So if we do that, we get, if you just use your calculator, you'll end up getting the measurement of angle B1 is 57.66 degrees. Okay. Um, just a heads up, this will always give you the acute angle. You will always get the acute angle here. Doing this process, you'll never end up with the obtuse angle. Again, that's because you're doing an inverse sine, and the inverse sine will always give you an angle in the first or fourth quadrant. All right, so we found B1. We need to figure out the other parts of our triangle. So maybe let's go ahead and redraw our triangle just using the labels that we're using here. So we have A, we have C, we have B1, we have side A, side B. This is going to be side C1 on the bottom, okay? Because we don't know what it is. And we're also going to have to find angle. It was C, but it's actually going to be angle C1 as well. So angle B1, angle C1, and side C1 are all for this specific triangle. Okay, so we now know angle A is 50, we know B1 is 57, so we can find angle C1. So it's going to be 180 degrees minus angle A, which is 50, and then minus angle B, which is 57.66. Angle C1 is going to be 72.34 degrees. Okay, and all that's left is side C1. And so we're going to have to use our law of sine again. So the sine of 72.34 over side C1 has to equal the sine of, which pair did we have first? We knew we were given A and A. So the sine of 50 degrees over 68. And so if we compute that, so again, that's cross multiply and divide. We're going to get side 1 is equal to 84.58. Again, just checking things. Angle A was 50, B is 57, and C is 61. So C is the largest angle, and its side is 84, which is longer than the other two, right? So my proportions are matching up. Angle B, A was the shortest or smallest angle, and side A is the shortest. So the work that we have so far for this first triangle looks like it's correct. Okay, we were given angle A, side A, and side B. We found angle B, we found angle C, and then we found side C. All right, so that's again the right triangle, the whole triangle. We have to do the same thing using the left triangle. Okay, so again, let me sort of draw what the left triangle here is going to look like. Compared to the whole thing. Okay, so here's angle B1, which we already found. Here's angle A. The top was angle C, but now it's going to be C2, and the bottom side is going to be C2. We have this obtuse angle inside. It is going to be B2. Okay, and we know that these two angles are equal to each other. And we already found this angle. We know angle B1 was 57.66 degrees. So how do we find B2? B2, again, we said that angle B1 and B2 have to be supplementary. So B2 is going to be 180 degrees minus B1. So that's 180 degrees minus 57.66, which means B2 is going to equal 122.34. Okay, so we now already have one of the angles for the second triangle. And again, notice it's an obtuse triangle, or an obtuse angle, just like the way I've drawn the picture. From here on out, it works pretty much the same. We still had angle A, was 50, and now we have angle B, so we can find angle C. All right, we know angle B plus, or sorry, angle A plus angle B plus angle C must equal 180 degrees. So what's that give us for C? Well, 180 minus 50 minus 122.34 turns out to be only 7.66 degrees. So it's a really small angle. This is, again, C2. So when you have a big obtuse angle, the other two angles can't be that large. Okay. If you add, check this up, if you add 122 plus 50 plus 7-ish, you're going to end up with 180 again. So they should add up back to 180. So we've now found, for the second triangle, all three angles. And then we still need to find just the third side. So we need to find side C. And it's going to work the same way it just did before. So we're going to take the sine of angle C2, so that's 7.66 degrees, over side C2. It has to equal the sine of 50 degrees over 68. And if we cross multiply and divide, we can find our last side. So it's going to be 68 times the sine of 7.66 degrees divided by the sine of 50 degrees. And that comes out to be 11.83. Okay. So, and we've now found both triangles. So we found the larger acute triangle. We are given angle A, and we found B1 and C1. And then we found the third side. And then we did it for the obtuse triangle. We found angle B, then angle C, and then side C. All right. And again, the relationship between these was this isosceles triangle that's created by the two sides of our given side here. And again, please remember, when we talk about all this work, the letters are meaningless. So A, B, C, it's just a way to reference the specific triangles or sides. You don't have to use A, B, and C. You could use P, Q, and R, or you may not even be given letters, or they could be Greek letters. So don't get so attached to A, B, and C that you get stuck when you get to other problems. All right, let's just look at an application here. Say we have a triangular plot of land that's being surveyed for future construction. And we're given the angles of two of the corners of the property. They're measured to be 38 degrees and 42 degrees. And then we're also, we go out and we measure the angle or the distance between those two angles. And we find that it's 150 yards. Okay. So first, what we want to figure out is what kind of triangle are we talking about. Okay. And to do that, again, we want to think about, let's first draw our triangle. And again, I'm just going to use sort of the same picture I've been using before, A, B, and C. And I guess I even flip the B and C location. It doesn't matter, just draw a triangle. And then label it and figure out whatever you want to do. We're told, let's say, I'll say angle A is the 38 degrees. And I'll say angle B is the 42 degrees. Again, I'm just picking A and B. I can draw the picture however I want. The main thing that you have to do is figure out where the 150 goes, and it says that it's the length of the edge of the property that's between the two angles. So that means it has to be this length from A to B. So this has to be 150 yards here, okay? Which this would be side C using my convention here. So we do not know side A or side B, okay? So what kind of triangle is this? Well, we're given two angles and the side in between them. So that would look like an angle side angle. Two sides and the angle in between, or sorry, two angles and the side in between. So next we want to find just all the measures of our missing angles and sides. So we need to find angle C and then sides A and B. So to find angle C, C is really easy. We know it's the sum of the other two. And then subtract it off 180. So C is going to be 180 minus 38 minus 42. So we know C, 180 minus 38 minus 42. So we know C has to be 100 degrees. 100 degrees. Okay. All right, so from now we can go ahead and find, we actually now have a pair. We have our side and angle C. We didn't have a pair before. So let's go ahead and find A. So for A, we have the sine of angle A, which is 38 degrees over side A. And that has to equal the sine of C, which is 100 degrees, over side C, which is 150 yards. So if we cross multiply and divide, and that comes out to be 93.77, and that's a length, so it's in yards. If we do the same thing for B, we're going to have the sine of 42 degrees divided by B, and that has to equal the same thing, sine of 100 degrees over 150 yards, which is 101.92 yards. So we've been able to find the missing angle and the two missing sides. The last question we want to look at is how do we compute the area? So again, to do the area, we could use the standard. Area is 1/2 base times height. And that totally works. The only problem with it is that we don't know height. We have three sides, but none of them are perpendicular to each other. So I don't know if we really want to do that. However, we are given two sides and the angle in between them. Okay, so in general, it's 1/2 A times B times the sine of theta. The A and B in the formula do not have to be the A and the B in the triangle I've drawn. Okay, they can be, but they don't have to be. It just means two sides and the angle that's in between them. Okay, so because I just want to emphasize this, I'm going to use angle A. So I'm going to rewrite this as 1/2. So if I use angle A, the sides next to it are B and C. So I'm going to use 1/2 B times C and the sine of angle A. So that's 1/2. The length of B we just found, that's 101.92 yards. Length of C we were given, it was 150. And we have to compute the sine of angle A, which was 38 degrees. And so we have to plug that into our calculator. So we have 1/2 times 101.92 times 150, and then times the sine of 38 degrees. And that comes out to be 4,706.12. And since this is an area, it's going to be in square yards. Okay, so we've been able to determine what kind of triangle it is. We've been able to solve that triangle, and we've been able to compute the area of the triangle itself.